All right, here we go. This is a tough objective, this limiting reactant one. Not only are we taking on stoichiometry, right? The idea that we're going to go from a reactant in grams converted to moles, which is key, right? Because chemical reactions are done in moles because moles tell us how many particles are reacting. We have to know how many particles are reacting. Mass is deceptive in that we don't know exactly how many particles there are. We just know the mass, the weight, right? How much they weigh, and each molecule is going to weigh different. And so we have to do chemistry in moles because it tells us number of particles essentially that are reacting. So a couple parts to this. We got to get a balanced chemical reaction because we will get to that, right? Once you get from grams to moles, then you need that molar ratio. In this case, we're going from our two reactants and then solving for the product carbon dioxide. We're not going to look into water in this one, but in this case, we're looking at carbon dioxide. Then you can solve for moles of carbon dioxide, and that will tell us which one is limiting. Whichever one forms less moles of our product, whether that was carbon dioxide or water, is the limiting reactant. Because a chemical reaction is just like baking or whatever, right? If you run out of something, the reaction stops, or you can no longer make more bread or whatever. So whatever forms less moles of the product is going to run out first. And then the other one, it won't form that many moles of the product. It would form as many as it could, and then it would have excess. So the problems in ALEKS can look at different things. It can look for how much is produced, which is what this one does, or it can look for how many grams of a reactant will be left, which could be 0. If it's the limiting reactant, that answer would be 0. If it's not, then you might have to, once you solve for moles, you're going to have to do a subtraction of how many moles were actually used of that reactant, and then solve that, and then how many are left over, and then convert that to grams. So lots of different ways this can be asked. This one is going to from solving for both reactants to a common product, and then converting the lowest amount to grams. So let's look at this. So we got hexane. I'm going to simplify that a little bit. We're going to write our balanced chemical reaction first. So this is C6, and then we have 8 plus 6, 14 hydrogens plus oxygen. This is a combustion reaction. It's going to form CO2 and water. Okay, so I'm going to start by putting a 6 here, because I need 6 carbons on both sides, and then I got 14, so I'm going to put a 7 here. Now, what I see is a 7. We got to balance oxygens. We got O2 on the left side, but that only can form even amounts of oxygen. And here we have a 7 plus 12. So I'm going to end up doubling everything. So in combustion, oftentimes it works itself out. If you have an odd number of carbons, so if carbon is 1, 3, 5, 7, etc., it works itself out without having to doubling everything. If it is even on the left side, you often have to double that fuel, which in this case is hexane. Okay, now I got 12 carbons, so I'm going to go with a 12 here. I have 28 hydrogens, so I need a 14 here. And now I have 14 plus 24, so 38. So I need 19 oxygens. So tough balance reaction. But now that we have that, we can do our mole ratio. So, okay, next thing is to start with 67 grams. Another key to notice here is hexane has 2 significant figures. Oxygen has 3. So if we end up that oxygen is our limiting reactant, then we have to solve with 3 significant figures. If hexane is, then we solve with 2 significant figures. So kind of a weird one with significant figures here. So 67 grams of our C6H14. We're going to do molar mass, grams to moles. And then we're going to go moles of our fuel into moles of CO2. And that's where we'll use this balanced chemical reaction, 12 to 2. Let's figure out our molar mass. So 14 plus 6 carbons, so 12.01 times 6. So I got 86.17 per 1 mole. So I can solve there. Let's write our other one out. 75.9 grams of oxygen, 32 grams per 1 mole. And then here we got 19 moles to that same 12. So this is that primary reason why we cannot just use mass. First of all, it's 86 versus 32, and then we have significantly different mole ratios. So I'm going to solve for moles of both. You could go to all the way to grams if you wanted, and just pick the grams that were less, but I like to go to moles and compare. 86.67 minus 80 divided by 86 times 12 divided by 2, I get 4.6652. And here I got 75.19 or 0.9 divided by 32 times 12 divided by 19. 1.498. So which one is limiting? It is our oxygen. We have almost 3 times as much, or a little over 3 times as much hexane as we do oxygen in particles, not in mass, but in particles. So even though it's a higher mass, 75.9, it is the limiting reactant. And so now to finish this up, because this one is about product, so we don't need to compare the reactants at this point. We're going to go every 1 mole of CO2 has, I believe it's 44.01 grams. And so I got 65.928 grams. Now again, oxygen up here at 3 significant figures. So I'm going to answer this one in 3 significant figures, which is 65.9 grams. Now, if the question does ask you to compare reactants, you might have to, okay, how many moles were actually used? And then how many are left of a certain reactant, and figuring out and then multiplying back to grams. So lots of different ways to answer this again, or ask this. There we go. But the big takeaway here is that we had amounts of both reactants, and we had to figure out which one is limiting the reaction, which one will run out first.